Okay, so the last slide introduced you to the idea of, or the last video introduced you to the idea of KSP, as well as how to figure out KSP from given values. We're going to start this part of the video taking a look at how we can calculate solubility given what the KSP value is. So we're going to work backwards. Okay, so we are given that KSP for nickel carbonate is 1.4 times 10 to the negative 7. So we want to know what the molar solubility, that means how much of the nickel carbonate is actually going to dissolve when you get a saturated solution. So the S is the change in the nickel carbonate. How much do we have? Since it is a 1-to-1-to-1 ratio, we are going to lose a certain amount of nickel carbonate, and we're going to gain that exact same amount of nickel ions and carbonate ions. So at equilibrium, this is a reasonably simple problem. We're just going to have S and S. So we know what KSP is. We know how to set up the equilibrium expression, nickel ion times carbonate ion concentrations. So the KSP is really equal to S squared in this case. And so we've got S then is equal to 3.7 times 10 to the negative 4 molar. So this is a very simple question, but what if you get into something a little more complicated where S is, it's not just 1-to-1-to-1? Okay. We can continue that idea from the nickel carbonate and go into how much solid would you wind up with. So let's say that the solubility of the nickel carbonate was 3.7 times 10 to the negative 4, like we found, and we have 500 milliliters of solution. So we want to know what mass of nickel carbonate was needed to make that saturated solution. We can figure it out. We've got the molarity, we've got the volume, so we can figure out how many moles of nickel carbonate was required to do that, which means we can then figure out using molar mass how many grams of nickel carbonate was required to do that. So KSP can go on to be used in mole calculations as well. So what do we find out? In order to make that saturated solution, we would need to dissolve 0.022 grams of nickel carbonate in 500 milliliters of water to get that saturation point. Okay, so here's here's a question like I was alluding to earlier, where you have not a 1-to-1-to-1 ratio of ions. So it gets a little more complicated. So here's our equation. When you fill in the ice chart, you're losing MgF2, gaining an equal amount of Mg ions, but you're gaining twice the amount of F minus ions. So that's going to make your KSP expression a little more complicated. So I have S for magnesium, I have 2S for fluoride, plus remember, I've got a 2 here, so I need to square it. So again, I really have 4S squared times S, which is 4S cubed. So then KSP is equal to 4.7 times 10 to the negative 11. And what is the solubility product constant? Remember, this we had to look up. This was given to us, even though it wasn't given up here in the problem. This we had to look up. So what's the actual solubility? So we know that magnesium fluoride, to create a saturated solution, you need to have 2.6 times 10 to the negative 4 moles per liter of magnesium fluoride dissolved. How many grams is that? Well, you can see very similar to what we did the last time, a very simple mole problem to get us back to grams of magnesium fluoride. Okay, next idea is the idea of the common ion effect. What if I had magnesium fluoride in something where it wasn't just pure water? Okay, so that's the situation. If I'm putting the ionic substance into a solution where there are already ions present, especially a common ion present, that's going to change the solubility. So the more common ion is already in solution, notice that what happens is the solubility of the magnesium fluoride decreases. So the more F minus that's already around, the less of this is going to dissolve. And hopefully that makes sense if you think about Le Chatelier's principle. If I already have F minus around, it's going to drive the reaction back to the left. And so here's the explanation for that. So we've got this equation. The presence of the common ion is in a solution is going to lower the solubility of the salt. Here's our dissociation equation. But if we already have some of this around, the amount of this that's going to dissociate will be smaller. Le Chatelier's principle is going to keep this quantity from getting as big as it should because there's already some of this quantity around. Okay, so the addition of a common ion will shift the solubility of equilibrium backwards. This means that there will be more solid salt in the solution, and therefore solubility will be lower. So let's say we've got this situation. We want to calculate the solubility of magnesium fluoride if I already have a solution of 0.080 molar NaF that magnesium fluoride is going into. So this should all look the same except for the F minus column. I already have 0.080 molar of fluoride. So as magnesium fluoride dissociates, I get 1 mole, or I get 1 magnesium ion, but I get 2 fluoride ions. And that's got to be added to the quantity that I already had to start with. And so at equilibrium, that's how much F minus I have. Okay, so putting all my numbers in, my constant is still the same, 7.4 times 10 to the negative 11, but this becomes a little more complicated. Now, we're back to equilibrium expression, so I know you guys have the calculator that lets you solve, and you can absolutely 100% use it in this case. But if you think practically, since Ksp is so small, the amount that's actually going to dissociate, this number is so little, the amount that's going to dissociate is so much smaller than the amount we already have that we can assume that the amount you still have is that. So we can simplify it, and that way we wouldn't have to use the complicated solve function because we can get rid of that plus 2x and wind up with a concentration of 1.2 times 10 to the negative 8th. And if you remember, that is a smaller number. This is a much smaller number than what we had in the previous situation where there was no F minus already present. Okay, so generally it's fair to say that salts with very small solubility product constants are only sparingly soluble in water. Yep, we know that. When you're comparing the solubility of two salts, however, you can sometimes just compare the relative values of their Ksp. That works, however, only if you have the same number of ions. So you have to think about the dissociation equation. How many total ions are you getting in solution? So for example, I have CuI has a Ksp of 5.0 times 10 to the negative 12. When this dissolves in water, what do I get? I get 2 ions. Calcium sulfate has a Ksp of 6.1 times 10 to the minus 5th. Again, I get 2 ions when I put this in water. So the fact that each of them gives me 2 ions means that I can compare these Ksp values directly, and I can say that the calcium sulfate is much more soluble than the copper iodide. However, if you look at a situation like this, you look at the Ksps and you think, oh, well, Bi2S3 has a much lower Ksp, which means it's less soluble. But you've got to remember how many ions you're getting. Here you're getting 2, here you're getting 3, here you're getting 5. So when you solve for the solubility, when you solve for the amount that's actually going to separate the minus S idea from those last ice charts that we were doing, you wind up with a solubility that is much larger for the Bi2S3 because it gives you, because you have 5 ions being generated. So be careful. The only time you can compare these numbers straight out is if the number of ions being generated by that salt are equal. All right, we're going to quit here because the next slides that we go to are going to be something a little bit different as well.